and I assume this has been, modulo the recording problem, the acoustics have been working fine for the recordings, right? You haven't been having issues.
These mics are good. We've had it at different volumes in the room, but
How much of it is coming back into the room? I never hear any echo, so I can't even tell that it's running.
as far as I know, it's fine. Are you ready whenever?
Oh yeah, absolutely.
Well, good morning, everybody. Just a reminder that we're going to hold our photo right after Liam's session. So we'll just walk right out. We'll take a short walk outside, get a photo taken, come back for the rest of the coffee break. So with that, let's turn it right back to Liam McAllister.
Thank you, Oliver. Good morning, everybody. So brief recap on where we are. Lecture 1, we talked about vacuum solutions. Lecture 2, we talked about classical flux compactifications, but mostly in 10 dimensions. And today we're going to switch down to 4 dimensions, study the 4-dimensional theory, first of classical flux compactifications, and then we're going to include quantum effects. So up here is the story as I wrote it last time. This was the story of last lecture, and let's just run through it and make sure the logic is clear. So in lecture 1, we first talked about vacuum solutions, empty Calabi-Yau compactifications, preserving n equals 2 supersymmetry. And by empty, I just mean no stress energy, pure geometry. The problem with those theories is that they have moduli, too many moduli, and are ruled out by cosmology in various ways. Flux compactifications are a specific class of non-vacuum solutions in which the stress energy of quantized flux changes the metric and the other field. Now, what I showed you last time by manipulating the Einstein equations and Bianchi identity for type 2b supergravity in 10D is that if you compactify type 2b on a Calabi-Yau threefold, you can't find an interesting non-vacuum flux compactification solution unless you have sources of negative tension and negative charge. And the negative tension and negative charge have to be equal. So what we found is that in type 2b compactified on orientifolds of Calabi-Yau threefolds, that is to say, you take a Calabi-Yau threefold and you mod out by an involution, a geometric action on the space, which you can think of as approximately folding it in half or the like, combined with world sheet parity reflection, that's an orientifold, and it creates fixed loci called orientifold planes. In an orientifold with O3 planes and O7 planes, the charge and tension of the O3 planes is exactly what's required to lead to a non-trivial warped flux compactification. These are special conformally Calabi-Yau solutions. What that means is that the prefactor, the metric in the internal space is a warp factor times a Ricci flat metric. And the flux is imaginary self-dual. That means it's an I eigenstate of the Hodge star. And in these solutions, the complex structure moduli and the dilaton get masses classically. You just look at the 10-dimensional action and you see the complex structure moduli and dilaton appearing with coefficients flux squared. So if the fluxes are non-zero, those fields generically get mass. Okay, that's what we figured out last time. Now, before now switching over to talking about the 4-dimensional EFT that results, let's first see if anyone has any questions about that story. Yes?
If there's objects that have seemingly negative energy, why is my theory not unstable to the nucleation?
Very good. Question is, what about the negative tension of these objects? So the leading problem that you encounter with a negative tension extended object is that it can, in principle, propagate modes with wrong sign kinetic term. Orientifold planes have reflecting boundary conditions such the ingoing and outgoing modes are canceled out, and there aren't any propagating degrees of freedom. They're totally rigid. So they're not dynamical objects at all.
I think the question was about just like nucleation of more. Exactly.
Yeah. Okay. So these are you're not actually lowering some. Yeah. Okay. So no, this is a good question. So you would need to. I mean, in order to conserve the various charges, you would need to have these objects and anti-versions of those objects, which would then have which would not necessarily. Okay, I have to think of what the best argument is for this, why they can't be pair created. Yeah, the starting around a background and considering small fluctuations, there are no instabilities, but yeah, in principle, I mean, in certain orientifold configurations, there can be non-perturbative instabilities. In these ones, we're going to end up preserving supersymmetry, and so there isn't such a decay mode. Yeah, good. Yes, please.
Basic question, which is the first lecture, the vacuum solutions, the metric, the answers didn't have a warp factor.
Yeah.
Then we introduced the warp factor yesterday.
Yeah.
Is it like needed to like support this like quantized flux, or what's the logic behind it?
Yeah, very good. Okay, so the question is, why did we introduce a warp factor? There are two reasons. One of them is looking forward, and one of them is just to try to solve the equations. The looking forward one is that in the long run, we're going to want to break supersymmetry with an antibrane, and we're going to use the warp factor in the spirit of Randall-Sundrum to suppress energy scales in the infrared region of a warped throat. But that's sort of a wish kind of thing. As far as solving the equations of motion, one equation that I wrote out last time was a Poisson type equation. And the Poisson type equation looks schematically like Laplace, e to the minus 4a. This is the warp factor is g dot g bar with some prefactor, some m tau and a number, et cetera. And the point is, you can't, if you haven't introduced this in the ansatz, then it'll be inconsistent. So the fluxes necessarily cause warping. You can see that through this equation, for example. Okay, great. Other questions about what we're doing? Yes?
Where exactly did we see that the complex structure moduli had got masses?
Yeah, so we didn't see that in a particularly elegant way. The action contains a term. Again, there's a 1 over m tau, et cetera. S contains a term minus g 10-dimensional metric g dot g bar. Okay, and this contraction, as we discussed, was made with the Ritchie-Flat metric in the internal space. And there's a remark, which is if you take this is a little confusing. I'll write sub 10 here and sub 3 here. So this big G is a flux, and this one's a metric. If you take the internal metric GMN to lambda GMN, then since there are 3 inverse metrics here, and after taking the square root 3 here downstairs, this lambda scales out. So the Kähler moduli receive no potential, or at least an overall dilatation receives no potential. However, the shape moduli, you can just write out a specific choice of some fluxes and then try and add a complex structure deformation. GMN bar goes to GMN bar plus GMN. You add some piece that's non-Hermitian, and then you can see easily enough in examples that there's a potential. Now this is very hand-wavy, and for 2 reasons. One is the best way of seeing that the complex structure moduli have mass is treating them as 4D fields, which is what we're about to do today. And I'm also going to punt on a direct calculation of the complex structure stabilization to next lecture, because next lecture we'll do it in extraordinary detail in a 1-dimensional sublocus in the moduli space. And so we'll see it gradually. What I hope you understand now is that morally there's some dependence on shape here, and so it stands to reason that they could get stabilized. Likewise, the dilaton appears explicitly both here and in the definition of G, and so it's pretty clear the dilaton will receive a potential. Now, where these things get stabilized is anybody's guess. You can't read that off from just staring at the Tindy action. Okay, great, questions? All right, so now let's do 4-dimensional things. What are we going to do today? So this is now the story of what's going to happen today. We're going to understand that the 4-dimensional n equals 1 supersymmetric EFT has a flux superpotential, where G is the 3-form flux and omega is the 3-0 form on the Calabi-Yau. And we'll run through this story, but the bottom line is we'll find supersymmetric ADS vacua. Okay, and so as the lecture proceeds, we'll understand one line after another of this. Okay, so first, if we're going to write down a 4-dimensional n equals 1 supergravity, I should tell you something about the structure of such theories in general. And then we'll slot this particular theory into that mold. So the multiplets we're going to be concerned with are so-called chiral multiplets. And these things contain a complex scalar. Well, they also contain a fermion because they're supersymmetry multiplets, but we're not writing the fermions today. We'll call these fields phi sub a, where a runs from 1 up to some number m, or something like that, which we haven't yet determined. This will end up being the number of moduli. So these are complex fields. And the action, so in the same way that the horrible action I wrote down last time can be derived, the structure can be derived strictly on grounds of supersymmetry, the same is true now. The action that I'm writing down can be established by reasoning about what supersymmetry can allow. And so what does it involve? It involves, okay, a kinetic term for the moduli field. Well, you don't have to think of them as moduli if you don't want. For the scalar fields, kinetic term, KAB bar, space-time derivative of the field, space-time derivative of the conjugate field, space-time metric. I haven't specified that it's Minkowski that we're in. Minus a potential, which I'll write V sub f. It's the so-called f-term potential, which is a function of the fields and their conjugates. In general, n equals 1 theories also contain so-called vector multiplets, but we don't need any, so I won't write them.
Are you imagining K depends on phi in general?
Yeah, thank you. So now what is this K? So KAB bar, I mean, you look at it and you say, well, that just looks like some kind of kinetic term. At least the index structure is that it's a kinetic term, but what is it? It's the so-called Kähler metric on the moduli space. And I'll use curly m often to denote moduli space. Kähler metric on moduli. If you think back, we talked about Kähler geometry in the first lecture, but then the thing that was Kähler was the compactification manifold, the 6 manifold. This is going to be a moduli space with dimension, I don't know, 200 or something. And a property of Kähler manifolds is that the Kähler metric can be obtained by differentiating with respect to the fields and conjugate fields a potential that's a real analytic function of the fields and their conjugates. Okay, I mean, e.g. there's a stupid a equal to zz bar for the complex plane. Okay, you could just think of coordinate z, and you can get the Kähler metric on the complex plane by taking the Kähler potential to be zz bar. But you can write down, yes, please.
You mentioned that this was true locally for Kähler metrics yesterday?
Very good, thank you. So the question or the remark is, I said this was locally true. That's right, you can locally, non-trivial, cannot do it globally. But this, there's an associated invariance under which the Kähler potential goes to the Kähler potential plus a holomorphic function of the moduli fields plus the conjugate of that function, because you're going to take one holomorphic and one anti-holomorphic derivative, and that gets wiped out here, and the metric is unchanged. Under that invariance, so this Kähler invariance is the sort of structure that's related to the gluing that you'll have to do from one patch to another patch. Okay, good. Now, what is VF? So VF is the F-term potential. What's an F-term? Gonna write out the auxiliary component supersymmetry multiplet haven't seen it before, you can just file it away as a particular source for supersymmetry breaking effects. For us, there's just the potential. Well, what's the structure of this potential? It's equal to, again, this is something that comes from structure of supersymmetry, e to the Kähler potential over m Planck squared. I'll get rid of the m Plancks in just a minute, but we need them just to make a brief dBW bar. I'll tell you in a minute what the capital D's are. Minus 3 times 1 over m Planck squared WW bar, where W is called the superpotential, and it's an extremely important object, and it's a holomorphic function of the field. Well, okay, it's a section of a bundle over the moduli space, but it's a holomorphic one. And what is this DAW? DAW is defined to be partial phi A plus partial phi A of K acting on W phi. It's plain old partial derivative with respect to the coordinates, and then also a derivative of the Kähler potential instead of a derivative acting on W. This derivative hits the K and doesn't proceed as a derivative onto the W, in case the notation's not clear. This is called the Kähler covariant derivative. And the meaning of it being Kähler covariant is that under this transformation, if I take W goes to W e to the minus F, then this whole potential is invariant and well behaved. Okay, so if I had some sort of possible symmetry structure under which there's an ambiguity in how I presented my physical metric, I better make sure that my potential respects that, and it does. Okay, so this is the structure of an n equals 1 supergravity theory, at least in the sector of chiral multiplets. It's characterized by two functions. A holomorphic function and an analytic function. Now you can see that the analytic function k, the Kähler potential, is the only thing that matters for determining the kinetic terms. But the superpotential is quite crucial in determining the scalar potential. Kähler potential also shows up in the scalar potential. Okay. Now, just a remark at this high level before we get into the weeds of type 2b compactifications. The structure we're going to be using in lecture 4 to build a de Sitter vacuum is to make endless use of the fact that the superpotential is holomorphic, and therefore it can only receive holomorphic corrections. That strongly limits the kind of quantum corrections it can get. It does get them. We will write them today, but they're limited and controlled. And so what we're going to try to do is find regions in the moduli space where the vacuum structure, the scalar potential, is controlled by the form of W. K shows up, but we're going to find ways to insulate ourselves from unknowns in K. Okay, so the way you should think about this is the leading order classical data of K and W. If you know anything about a particular theory, you'll know what those are. But maybe you have no idea what the loop directions are to the Kähler potential. Okay? All right, that's the general structure. Now let's try and fit the theories that we've been working with into this mold. Any questions about n equals 1 supergravity in general? Okay, so what fields do I have? So what do you need to know in order to specify an n equals 1 supergravity theory? You need to be able to specify the superpotential, the Kähler potential, and of course the fields. And the fields we actually figured out last time and the previous time. What are the fields? They are Gij bar and C mu nu ij bar and C0 and plus I e to the minus phi, which is called tau, and Gij and G I bar J bar. Now, if you paid close attention previously, you might say that looks like half the fields he had before. Yeah. I was writing hypermultiplets of n equals 2 supersymmetry that have 4 scalars, and the orientifold cuts that in half. it gets rid of half the fields. And so I won't waste your mental space by rewriting the fields that get killed by the orientifold. You can look back in your notes and see that they're gone. These are the ones that are preserved by the orientifold. So after orientifolding, n equals 1. So as it should be, these are complex scalars. This is a pseudo-scalar and a real scalar, so together a complex scalar. This is H21 complex scalars. This is one complex scalar, and this is H11 complex scalars. So the Kähler moduli are complexified by the 4-form potential. Yes? Yeah.
This H is that how many of the G's as metrics or that exist, or is that including the counting that the I and J's can take different values?
Thank you. So here, for each 1-1 form, there's one of these and one of those, and together, if you think of them that way or something like that, this is the real part, that's the imaginary part. And so you get one complex field for each H11. Here, you get 1. And then here, for each H21, you have one of these and one of those, which respectively form the real and imaginary parts of a complex scalar. Was that the question? Sorry.
No, my question was like I takes values 1 to 3, right? Something like that.
Yeah, okay. But I see that I've written this in a confusing way. Let me call it delta Gij, and delta C mu ij, where I am going to take this to be proportional to a harmonic 1-1 form. So even though the metric itself the indices can only run it from 1 to 3 and 1 bar to 3 bar, there's lots of deformations with the metric. And those are counted by harmonic forms.
I see. So what we're counting is like the coefficient up in front of it.
Yeah, yeah. Yeah, sorry about that. This is not just, right, because otherwise you'd just be counting the components of a 3x3 Hermitian matrix, which is not going to get you all the way here. Yeah. Good. Okay, these are our fields. Yes?
Are these like the same as yesterday, but you take complex values?
Question is, are these the same as yesterday to take complex values? This field we encountered yesterday, the axiodilaton, in exactly this form. These fields we spent more time on the previous lecture, in lecture 1. These are the so-called Kähler moduli and complex structure moduli. And to be precise, these are the complexified Kähler moduli, because I've complexified them by this form. Was that the nature of the question, this complexification, or please ask again?
So what you say is half of it, this is like, yesterday we had like a double of that amount, but then
We also had, for example, these guys. I'll write in yellow the ones that you don't need.
so this is because you have already taken the quotient.
Yeah. In white is the stuff after the quotient. Yeah, correct. And in particular, these suckers here formed an n equals 2 vector multiplet, which has a complex scalar and a vector. And the projection keeps the complex scalar part and wipes out the vector, making a chiral multiplet of 4d n equals 1. Okay, great. Other questions about the structure of the fields? These are going to keep coming back over and over again, these particular fields. Okay, maybe we should pause a minute and have a conversation about how you interpret them. Okay. Let's first denote them, okay? I'm going to write these as z sub a, where a runs from 1 ... h21. And because most of the action is going to be happening in the Kähler moduli sector, I'm going to assume that h11 is equal to 1 for most presentation purposes, although certainly not in our papers, which is the problem. But for presentation purposes, I'll assume there's only one Kähler modulus, so I can write all the formulas for you. Right. Complex structure moduli, we won't do too many calculations with them till tomorrow, so it's going to be okay to assume there's a lot. Now, what is the interpretation of these things? The axiodilaton is a complexified string coupling. This is an axion, and this is 1 over the string coupling. Remember, a to the minus phi is 1 over g string. And roughly speaking, you think about Kähler moduli as representing the sizes of 4 and 2 cycles. Even dim cycle sizes, and complex structure moduli tell you about the 3 cycle sizes. So, if you've got a 6 manifold, you have to tell yourself how big are the various cycles of various submanifolds of various dimensions. There aren't any one-dimensional submanifolds, but you've got 2, 3, 4, and 6. 2 and 4 are counted here, 3 is counted there. So often people call these ones size and these ones shape moduli. Yeah?
Do the fermions play any role here?
Yeah, but they don't play a role in the classical solution that we're going to find. And so what we're going to do is derive the theory of the bosons and find supersymmetric solutions by solving particular conditions that I'll state later. And in those, the fermion and boson masses are matched, except for the fact that we'll be in ADS, so they'll be split by an allowed amount. So, but the fermions are only behind the scenes for present purposes, which is nice, because there's no way we would get through these kinds of calculations in even 20 lectures if we had to write all the fermions. Yes?
Sorry. So this is like saying you have a different action, but then the manifold is like, sorry, the orientifold is the same. So that's why it's the same as last time.
Yeah, okay, let me try and comment on this in a slightly different way. So we had, here's our Calabi-Yau, and then an associated moduli space of the Calabi-Yau at the n equals 2 level. Now what we're going to do is we're going to take this thing and we're going to fold it. I mean, you don't literally fold it, but you find an involution like this, and you pop these 2 sides onto each other, and you introduce some flexes, which I'll draw like this. And when you do that, the moduli space, very, very schematically is reduced. M and M prime, X and X prime, which is defined to be X mod the orientifold. And so we have here a moduli space parameterized by n equals 2 multiplets, vectors and hypers, and here by only n equals 1 multiplets, only chiral multiplets. So 4 scalars here, 2 scalars here, multiplied by these Hodge numbers. Was that the question?
So this action is just
This action or that action?
that action.
Yeah.
So is that related to the thing yesterday or just not related?
Yeah, okay, good. So the question is, how is this 4-dimensional action related to the 10-dimensional action that I wrote down last time? The answer is, the purpose of today's lecture, or the first 2/3 of today's lecture, is to show you how if you take the 10-dimensional action from last time and dimensionally reduce, namely integrate over all of the modes in the internal space, keeping only the 0 modes, because those are the only ones that show up in the low energy EFT, this is the resulting EFT, with the fields being these fields, and with the Kähler potential and superpotential that I will compute for you. So let me repeat that, because that's actually the whole story. Last time we worked in 10 dimensions, we solved 10D classical equations of motion. We found a flux compactification. We want to work in 4D. We need to do Kaluza-Klein reduction. Kaluza-Klein reduction consists of taking the 0 modes in the internal space and seeing what the couplings are of the fields in 4D. By n equals 1 SUSY, the structure has to be like this, but what we haven't determined yet is what are, well, in general, you need to know what are the fields, what's the Kähler potential, and what's the superpotential. We figured out what the fields are. In the remainder of the lecture, I have to tell you what are the Kähler potential and superpotential, and how do they come from the data of the 10D theory that we had last time. But that's a direct computation. Yes?
Is there a significance to the particular Kähler modulus you want to focus on?
Yeah, okay, good. Question is, is there a significance to the particular Kähler modulus you focus on? If there's only one, then it is the overall dilatation of the space. It dilates everything uniformly. It's this mode lambda that I talked about before, when I was talking about an overall rescaling. And it sort of carries the whole story. Yes?
Just a follow-up question. So you start with n equals to 2 in d dimensions, d equals to 10 dimensions.
Yeah.
Right? You reduce it to d equals to 4.
And you keep n equals 2 and d equals 4 because Calabi-Yau is preserved, yeah.
Yeah. And then you do an oriental folding to get n equals to 1.
Yes.
Super. Okay.
Yeah, I mean, you can describe the orientifold in 10D n equals 1 terms also if you want, but you could also describe it in 4D n equals 1 terms, yes.
n equals 2 supersymmetry in 4 dimensions is a lot less than n equals 2 supersymmetry in 10 dimensions.
Yeah, exactly. So we only ever had 8 supercharges in a Calabi-Yau compactification, not 32. And now we're only going to have 4 supercharges in 4 dimensions. Okay. So I need to tell you something about these objects, right? How do we get k and how do we get w? But if you stare at this thing, the key place where k shows up is in the kinetic terms. So our sort of idea is maybe we can calculate the kinetic terms directly and use that to figure out what the Kähler potential should be. Okay, so now let's compute the Kähler potential. At least the Kähler potential for the overall volume modulus. So the 10-dimensional action contains a term that you're very familiar with, just Einstein-Hilbert, like that. And we're going to write ds squared is eta mu nu. Since we're still looking at mostly stuff, we can carefully patch in ADS later, plus e to the 2u of x gmn dym dyn. You may say, what is this u of x? This is the so-called breathing mode. That describes an overall dilatation of the space. For example, suppose this is a fixed 1 in some units. Then e to the 2u tells you as you move around the space, so you know, here we are, and the Calabi-Yau has one size here and a different size there because the vev of u is different here from there. That's what is meant by this breathing mode. Okay? We want to calculate the kinetic term for this breathing mode. The kinetic term descends from this. It's a pure gravity thing. If you're eagle-eyed, you'll say, wait, didn't he have warping? Oh, don't do it, don't do it. It's going to take, yeah. There were some long-suffering people who did all this, and it works, but we don't want to go there on the board. Yeah, no, but if the question is, didn't you have warping, and isn't that going to affect the breathing mode? Oh, yes, it does, but yeah. At the end, it all boils down to something fine, so we'll leave it like this, but yeah, very good. Okay. So how do we do this computation? Right now, this is just a theory of gravity. We're just taking 10-dimensional Einstein gravity and dimensionally reducing it to 4-dimensional Minkowski space on some internal space with a not really specified metric. And I'm asking, what's the kinetic term for this field? It's a field, right? It changes in 3+1 dimensions. Well, when you dimensionally reduce this thing, so let's just do the integral, okay? We're going to get the integral over the internal space, the metric on the internal space. Then there's going to be left over square root, no, minus, well. I'm going to write square root that minus eta just because I feel bad not putting in the measure factor, but it's just Minkowski, okay. d4x. And then there's going to be r4 e to the 6u of x, r sub 4, plus additional terms. Where the additional terms come from, for example, the Ricci components in the internal space, which might be non-vanishing. But the kinetic term only comes from here. So you look at this thing and you say, that really looks like, okay, this is just some reference volume, which I'll write v sub ref, okay? So of some fixed metric. And this is a theory of Einstein gravity coupled to a real scalar. And it's coupled to a real scalar in such a way that this theory is not written in 4D Einstein frame. In 4D Einstein frame, the action is Einstein-Hilbert plus scalars. This is Einstein-Hilbert times a scalar, and there's no kinetic term for this scalar yet. So this is a scalar tensor theory in Jordan frame. What do you do with it? You perform a conformal rescaling, a Weil rescaling, to take this to Einstein frame. Okay, so you use, so exercise, use the standard formula that under g tilde mn in some dimension is e to the 2 omega of space-time position, gmn, e to the 2 omega Ricci scalar tilde is Ricci scalar minus 2 dimension minus 1 Laplace of omega minus dimension minus 2 dimension minus 1 nabla omega squared. Okay, so this is like, standard formula in, I don't know, it's in Wall. in Burrell and Davies, even Joe quotes it. It's just the conformal transformation property of the Ricci scalar. And when you perform a Weil rescaling to bring this thing into Einstein frame, that rescaling is going to spit out a kinetic term for U with some coefficient. Right? Because in Jordan frame, there's no kinetic term at all. There's no derivatives acting on U. But this isn't the Einstein frame Ricci scalar. It's the Jordan frame Ricci scalar. Perform a Weil transformation to get over to Einstein frame, and you will shoot out a kinetic term. Exercise use below to compute the prefactor, which is, I mean, it's just a number. The number is going to be 24. I'll show you in a minute. Yes?
Jordan frame the same as string? No, is that something
Yeah, sure. I mean, sometimes people, okay, a scalar tensor person would just say Jordan frame. String frame specifically, people mean either as an e to the minus 2 phi with phi the dilaton.
which is equal to the G string?
Yeah. And here, what we're talking about is a different thing. This is a breathing mode, not the dilaton mode. So that's okay. So that's an exercise you can do. It's a reasonably, it's a completely straightforward thing to do. And what's the result? So the result, I put this here so that, well, to hopefully demystify a little bit of the computation of the kinetic terms, because this is just gravity reduced on some space, and actually the properties of the space don't matter. All that matters is that it's a space of dimension 6. You just do Einstein gravity from 10 to 4, and you get a kinetic term. So result, which is the exercise, S4 contains in Einstein frame, okay, m Planck squared over 2 integral d4x square root minus, I'll just still write it as eta just to remember we're doing flat space. Okay, let's just write it as g. R4 minus, there's a half out front, and inside here there's a 24. d mu u, d nu u. Like that. So the kinetic term is that. So, okay, not too bad. Now, that's a kinetic term for a real scalar, and everything else we've been talking about has been complex. So the game now is to guess a k, and in particular, what you've got to do is you've got to somehow figure out a complex coordinate. We're going to define t to be e to the 4u plus I times the integral over the basic 4 cycle C4. When I say the basic 4 cycle, what I mean is we assumed H1 is 1, so there's only one 4 cycle class. So there's only one such integral. And I'll write this thing as theta. Now, previously I talked about complexified Kähler moduli, and I said they roughly speaking tell you about sizes. The real parts of the complexified Kähler moduli directly tell you about sizes. Look, that's a 4 cycle size, right? Because e to the 2u is the size of, is what comes up in the metric, so this is like 4 lengths. It's just complexified by a theta angle. Now, dt, what we need is that dt dt bar of k of t t bar is equal to minus m Planck squared dt dt k bar is equal to what we have over there, which is minus m Planck squared times 12 d mu u times d mu t d upper mu t bar equals d mu u. I should have an m Planck squared in there for these conventions. Okay. And so what am I doing? I take the form of the kinetic term that's forced on me by n equals 1 supersymmetry. I take some 10-dimensional field that I can break up into a 4-dimensional field and 10-dimensional stuff. I work out the kinetic term of some of it, and I try and guess what kind of complexification and what kind of Kähler potential would work such that the n equals 1 structure is the same as the thing I directly calculated. Okay, so it's guess. You guess the Kähler potential that gives the theory that you directly computed. Is the general logic clear? Yeah.
If this is the theory, this is the theory. So why do we need to put it into this other form?
Aha, very good. So the question is why bother to package it? Yeah. It's amazing how much more you can do once you've expressed it in the right coordinates. One of the things that you can do is once you've been able to express it in terms of good complex coordinates, you can use the fact, and we will use the fact today, that the superpotential receives no corrections. If you write, sometimes you can have a protected quantity and you write it in the wrong variables and it looks like it has all orders corrections, and then you're hurting yourself. And so that's what we want to do. We want to write it in a manifestly n equals 1 form. Yeah.
So I don't know why you want to comment on this later, but like, are we cheating a little bit by choosing the one moduli that we have like an explicit expression for? Or?
No, I mean, is it a cheat? It's a cheat for the purpose of putting it on the board, but then you can do the you can do the whole thing.
Since of all, like when I look up some Caviar, and as then like you also do like an explicit computation like.
In fact, it's actually pretty easy to do the explicit computation for more of these things. I mean, very schematically, because this overall breathing mode covers everything. And the only thing, but what I mean by covers everything, the thing that comes from the Weil rescaling Einstein frame is this overall breathing mode.
Yeah.
And then, as I'm happy to discuss afterward, you can try and write the total volume of the space in terms of all the other Kähler moduli. But it's only the one combination total volume that shows up here. And so that means that the Kähler potential at leading order has to be a simple combination, one single simple combination of all of the different Kähler moduli, and it's the combination that in the one modulus case reduces to this. But you can do an explosive computation too, and one does. What is not easy, and this is why, this is one reason why the work that we've done to be described in lecture 4 didn't happen until 2024, even though the idea that we're talking about came from 2003. It's not so easy to compute alpha prime and G string corrections to this. What we're talking about is the leading order thing, and that's just a geometry thing like, can you do it or not? And yeah, you can do it. The physics part is harder. And we'll come to that. Yes?
Confused a little bit. Do you mean that like doing this rescaling, you kind of get that kind of result which
Yes.
is on the right? That's what you do, starting with the metric on top, and then you do this, and then you kind of, here it's kind of implicit, and there you rewrite it more explicitly, like adding more terms, right?
Yeah, so good. So the question is, what is the relation between what happens over here and what happens over on the right? And the answer is, here we introduced a real degree of freedom and we found its kinetic term. And there we said n equals 1 SUSY tells us that all the degrees of freedom have to be in complex pairs. What's the pair? What's the partner? The partner is a theta angle from integrating the 4-form potential. And then what's the killer potential? Well, there's only one, I didn't tell you yet, equals, so there's a unique solution for this, which is that k is equal to minus 3 log of t plus t bar. And that's a super easy exercise to check that that gives the right number. So, I mean, what is t plus t bar? T plus t bar, I don't want to take all your fun. You should do it yourself. But this is e to the 8u. And then so this is just, so k is just minus 24 log u. And you can see it's going to work. Yeah.
2 e to the 4u.
E to the 4 e to, thank you. So now there's going to be a constant which we'll get rid of, and then 4 minus 2 e to the 4u, thank you. 2 e to the 4u, and then when we take the log here, we get minus 12 log u, and now it's going to work. Yeah, thank you. Very good. Okay. So this is the first piece of a big puzzle. I don't want to tell you all the other pieces on the board, but we succeeded in one thing at least. We figured out a part of the Kähler potential. We directly computed the Kähler potential for the overall Kähler modulus. And then you can do the same sort of thing in a slightly different way to work out the Kähler potential for the other degrees of freedom. But that's actually a little bit more tedious. Okay, but in principle, it's all controlled by the 10-dimensional geometry and 10-dimensional equations of motion. Okay, so that's the dimensional reduction story. Yes?
Potential would be the sum of the things you get for different quantities.
Exactly. So let me write that. And you know, it'll look sort of obscure, but it's checkable if you have a little bit of time, and I give the details in the notes. So the result, when you do this for all the fields, this is still for H11 equals 1, so 1 Kähler modulus. To save us some trouble, K is minus 3 log T plus T bar minus log of, okay, here's a weird one, minus I, the integral over the Calabi-Yau threefold, the 3-0 form wedge, the 3-0 form bar, minus log of minus I tau minus tau bar. Now, this last one you can easily check because I gave you the tau kinetic term in 10 dimensions, yes?
So you said we're integrating over the Calabi-Yau threefold.
Yeah.
Why are we not just doing the orientfold?
Very good, thank you. So actually, I'm going to elide that distinction repeatedly, but thank you. It's absolutely right. We're doing it over the orientifold. Yeah, what I should really say here is we're going to integrate over the compactification manifold, this thing. Now, this is a 6 form, so you can integrate it. And this is, one can check, and we can look in the notes. I'm happy to go through them with you afterward, that this gives a reasonable kinetic term. However, in view of trying to cut our way to the exciting physics here and not lose you in details, I'm not going to work with these Kähler potentials and kinetic terms very much. I'll just tell you how the stabilization works, and we'll do explicitly the stabilization in the Kähler sector. Okay, so we don't have to carry so much. Yeah?
It's a potential, so I can always rescale it. Does that rescaling have any meaning in the moduli space?
I just deleted the Kähler invariance here. And so if you shift K by K, yeah, so the question is what about rescaling K? And the answer is, well, if you're trying to get the normalization in 4-dimensional Planck units of something, then you better fix your normalizations. And so later, when I write, and I'm going to write a particular superpotential, and there's going to be a square root 2 over pi out front, and that's the only thing it can be. But for until you're trying to nail down an overall rescaling of the potential, there's no need. Yes?
So why are we integrating over the orientfold? I thought this term is sense from the n equals 2 vectors, and only like the vector gets projected, but not the scalars. So why do we integrate over the orientfold?
Oh, yeah, so, okay, so question, why are we integrating over the orientfold? I mean, the whole, you mean that there should be a factor of 2 or something coming in here? I think a fair statement is to get a Kähler potential rather than a pre-potential, you need to already be in an n equals 1 theory. And so it's only the orientifold that furnishes an n equals 1 compactification. Now, I'm going to play games in the next lecture where actually I tell you that I can get corrections to this that come from the n equals 2 theory and come from a pre-potential. And then I'll be sort of sneakily evaluating this more on the parent space. So the remark here was simply, was not that we're going to get a big difference depending on how we do this. It's just that what is the physical space now? And the answer is the physical space is the orientifold, not the covering space for the orientifold. Okay, so that's great. That's K. But now we need W, right? Because we need to know what the scalar potential is. Now, how do we figure out a scalar potential? Well, we have the scalar potential in 10 dimensions. And we have a candidate, I mean, I told you what the Kähler potential is. So the 10D S10 contains the following potential energy term, 1 over 2 kappa 10 squared, the integral of, now we'll keep the normalizations, 2 m tau, G3, wedge star 6, G3 bar. So that's the term that I keep pointing to and saying this is going to give a potential for the complex structure moduli. That's really the only potential term that we've encountered so far. So you can fit the pieces together because look, this is the general structure. And we've already figured out what K is. And we have a formula, which alas, I think, yeah, I deleted I erased the formula for the, I think, yeah. I have not retained the formula for the F-term potential, but it's an explicit formula in terms of W and K, and so you can ask, so to the potential that comes from 10D, we need W to take a particular form. Okay, so let me just repeat that. Vf in 4D is some Vf that's determined by K and W. And we know what K is. So if we know the left-hand side, if we know the potential, and we know K, we can deduce what W is. There are slicker arguments that Gukov, Vacua, and Witten gave, but I will just state what W has to be. It has to be up to an overall constant, which we'll deal with later, G3 wedge omega, again integrated over X mod omega. This is Gukov, Vacua, and Witten. It's the flux superpotential. Sometimes we'll write W flux so we remember. Now this thing is classical. It came directly from the 10-dimensional classical action. There's no alpha prime corrections. There's no G string corrections. It's classical and leading order. Okay. Now this is just a direct assertion, but you can check in the notes. We work out there how if you plug in these K and a test idea for W, you see this is the right one. All right, at this point, we have written down the structure of the 4D theory. Oh, I pulled too short. Yeah, good. That's the potential we need. Okay, so what are we going to do? We want to solve this theory and see what. Right. Any questions about the structure that we have so far? Okay, hopefully. Yeah, okay, now we've only understood the top line, but let's do the rest. The n equals 1 supergravity EFT in 4 dimensions has a flux superpotential given by this expression. So now let's try and solve. So if someone gives you a 4D n equals 1 theory, we want to find supersymmetric solutions of the 4D theory. These are configurations that are so-called F-flat. Where the F terms of some F term of some field phi is by definition this, the Kähler covariant derivative of W with respect to phi, which I remind you is the partial derivative of W with respect to phi plus d phi k W. And if you know rigid supersymmetry like flat space SUSY, but you don't know supergravity, this is a supergravity correction. This maybe you remember that the supersymmetry breaking comes from the derivative of W being non-zero, right? So these are the F terms. Now, if you know n equals 1 SUSY, you may say, what about the D terms? Well, remember, I didn't include any vector multiplets. So this is the whole SUSY breaking sector. So what we need to do is we want to solve d tau W flux equals 0, d complex structure W flux equals 0, and d Kähler modulus W flux equals 0. So that's our goal. We'll fail, but that's the goal, is to try to do this. Because if we could do that, that would be an n equals 1 SUSY vacuum. Okay, questions about this? I can say a word or two more about what we're doing if necessary, but yes?
The F term of phi, meaning we want to write down the BF there.
Yeah, okay, good. So what's the relationship between the F terms and the potential? So look over here. These are not kinetic terms. There's no space-time derivative. There's derivative with respect to the field. So these are potential energy contributions. This says that the scalar potential is a metric sandwiching F terms minus WW bar. And so if all the F terms are 0, then V is not 0 in general. V is minus 3 WW bar. Okay, and so what we're trying to do is find a solution where at least all of these vanish. Then you can preserve SUSY. Now you say, wait a minute, SUSY requires Minkowski. Flat space SUSY requires Minkowski. Curved space SUSY allows ADS. And this sign is negative. So if we succeed in getting all the F terms to be 0, then the potential will be negative, and the configuration will be supersymmetric, and we'll have a supersymmetric ADS4. Okay? That's what we want to do. Now, we won't succeed. But what happens? So again, I'm happy to say a little bit more about this, but I think the key point to take away is that we can solve these first two ones. At isolated points in the moduli space of these fields, moduli space of ZA times moduli space of axiodilaton, you can solve generically. And next time I'll give you an example of actually solving these conditions. So let me color code here. Isolated points. So then the ZA and tau are massive there. That's what it means for a point in the moduli space to be isolated. They have positive Hessian there. Okay, and so you should think that you have some a priori moduli space, which looks, I mean, forget about the metric on it, just look at a little patch. There's no potential on it in the n equals 2 theory, and then when you go to the n equals 1 theory, suddenly it has a complicated landscape, and you find local minima. Like that. Okay? Of this potential. Now we haven't yet talked about that. Okay? So what we've done, now, how do you see that this is plausible? Well, I mean, equation counting tells you it should work. Why is that? Because the superpotential depends on the complex structure moduli, encoded by this omega, and on the dilaton. It depends manifestly on both of those things. So if you've got H21 plus 1 equations that you got to solve, and you can explore an H21 plus 1 dimensional moduli space, and your objective function has generic dependence on your variables, you should be able to solve at dimension 0 generically. Okay, so there's an asterisk here, can generically solve. So typically you can do it. Typically, I mean, dimension counting, equation counting tells you you ought to succeed. But there's no T in the Gukov-Vafa-Witten flux superpotential. And so you add one more variable, T, and you try and solve more equation. The dependence on that new variable is not, counting no longer tells you anything. And we'll now be more explicit about that. Yeah, okay, good. So this is, the question is, how's omega related to z? It's honestly a little bit obscure, but you can, I didn't tell you this first of all, but you can write ZA can be defined to be the integral over some sigma A of omega appropriately chosen. So you can pick an appropriate basis of 3 cycles and integrate omega. These are the so-called periods. And those tell you what the complex structure on the space is. So these are good coordinates on the complex structure moduli space. Yeah. Thank you. Perhaps I should have said that, and that would have made this a little bit more plausible. So now, whenever you see an omega, you should think the complex structure we're hiding in there. Yes?
I guess 2 quick questions. Just struggling. So at this point, what assumptions have you made on the Calabi-Yau to do this compactification?
Okay, good. Yeah, let's step back. So what have we done? We first of all wanted Ritchie flat, Kähler, holonomy SU3, a Calabi-Yau threefold, no other special conditions yet. That was good enough for lecture 1. Now in lecture 2, we wanted to find an orientifold projection that would allow us to make non-vacuum solutions. Not every Calabi-Yau has nice orientifold involutions possible. So what you have to do is you have to go and find one. We find them. You find a Calabi-Yau that you can nicely fold and leave nice fixed point loci, so an orientifoldable one. And having done that, we're done. Anything else is going to be good enough. Now, it's not guaranteed that the solutions we find will be exciting, but all of everything I've described to you can be carried out. The restrictive assumption that I made for the purpose of presentation on the board is that H11 is one Kähler modulus, but that's for writing, not for physics. Yes?
Maybe I missed something, but I'm just a little bit confused. When I usually think of flat directions, I'm thinking of massless directions in my theory.
Yes.
So if we're solving this flat directions with tau and DZA, how are they massless?
Thank you, thank you. Okay, question is, what's the deal with these things being called F-flat? Actually, F-flat just means that the F term, which I've written in components here, vanishes. And there are associated theories where there are typically flat directions, but really, this is just, it's a terminology that's no longer appropriate here. It just means that the auxiliary component in the chiral multiplet, the thing that pre-multiplies a theta squared, is 0. And that means that the configuration is supersymmetric. So yeah, it would be much nicer if I just only ever called them vanishing F-term configurations, because then that wouldn't suggest they should be flat. And by no means are these flat. Not at all. Thank you for bringing it up. Yeah, good. Other questions? Yeah.
I think the board disappeared. At some point, I think over there you said something like, we're going to get an ADS4.
Yeah. We are.
And then I guess it's later you'll talk about how we're going to use that for consider.
Correct. Not today, though. Yeah, so good. So, right, so what's the story here? So, day 1, we talked about empty Calabi-Yaus and we saw they had a moduli problem. Day 2, we realized if we could put flexes in them by orientifolding, maybe we'd get rid of some of the moduli. So far, we've seen we can at least get rid of the complex structure we just saw 1 minute ago. We can get rid of the complex structure moduli in axiodilaton, stabilize them at isolated points, no flat directions left. We have a leftover Kähler modulus. Remainder of today, we'll talk about how, by including quantum corrections, we can stabilize that too. But we're going to stabilize it initially supersymmetrically. The end of today, we'll find a supersymmetric ADS vacuum, which is not what you want in the long run, but it's what you want to build on. And then the point of tomorrow is to explain how you can break supersymmetry in that setting. Okay, so this we can solve, but this one doesn't look so obvious. Let's just write it out. So if the complex structure moduli in axiodilaton have gotten mass, it's actually pretty high mass, because we put in some quantized fluxes in a not so big Calabi-Yau, and there's no reason for the associated scale to be super duper small. So these are pretty heavy. We're going to integrate them out and look at the EFT below. So below mass scale of the complex structure moduli and the axiodilaton, W flux, which was a function of the ZAs and tau, goes to its VEV, which should be the superpotential evaluated on the stabilized VEVs of these things. In other words, the thing that I was denoting by that like red point. You go to that point in the moduli space and you evaluate the flux superpotential, and we're going to call that W naught. So, a superpotential has dimensions of mass cubed, but other than that, it's a number. This is some number, and the EFT now only has the following degrees of freedom. The only field is T. K, we derived, is minus 3 log of T plus T bar, and W is W naught, which is a constant with respect to T. Constant with respect to the T field. Let me just not write that because it's too gross looking. So now we have a theory of a single field with a nice log Kähler potential, superpotential, so we can definitely analyze this thing.
Stabilizing somehow we would also want to check the second derivative somewhere, right? Like
Absolutely. So I implicitly did that. By implicitly, what I mean is when I show you an example tomorrow where we do it explicitly, I'm going to check. And when I say that we can stabilize these things at isolated, well, first, here's another thing. If you solve these conditions, they imply that you found a minimum, but not every minimum is of that type. They imply that you have found a stable solution. You can have a so-called BF allowed, Brighton-Loder-Friedman allowed tachyon because you're in ADS, but the solution won't have any instabilities because I've arranged for supersymmetry for these fields. Now, we're going to break supersymmetry in a minute, so hang on, but the short answer for right now is all of the points that I'm going to be talking about and denoting like this are actual Hessian positive points. It's not obvious. You have to do a calculation. Okay, so we have some EFT, and we know what to do in this theory. We compute the F term. dTW. And what is that? That's partial TW, I mean, just from the definition, plus K, let's just write it as dTK W. And this is dTW naught, which is a constant. And this is minus 3 over T plus T bar W naught. And since W naught is a constant with respect to the Kähler moduli F term is given by this expression, minus 3 over T plus T bar W naught. Equals 0 only if, well, T plus T bar goes to infinity, or W naught equals 0. All right. And this we don't want to do. This is decompactifying to 10 flat dimensions. That's boring. It's obvious you preserved SUSY back then because you just diluted away all the sources and you're back to 10D 32 supercharges. W naught equals 0 is not completely obvious, but equation counting suggests there's no reason for the VEV of the flux superpotential to be 0, and in general it isn't. And also that's a sort of a special subcase that doesn't give us the sort of structures that we want. And so dTW is not equal to 0 generically and in all the cases that we care about. And that means that supersymmetry is broken by an F term for T. And that was our condition for supersymmetry to be preserved, which was that the F term should vanish. Now let's calculate the potential. Something interesting is going to happen in the potential. Again, I won't spoil your fun. You can do this. Just plug in this T, and you can check that the F term potential is actually 0. This is called the no-scale property. And as a consequence, T not stabilized. So this is related to the questions about flat directions and Hessian, et cetera, before. If you just go ahead and compute the F term potential with these data, okay, the formulas are all shown on the board. It's a trivial exercise. And all you have to do, when you do that calculation, what's going to happen is that some of these terms, well, that term, and you'll get 0. Now, I don't want to spend all the remainder of the lecture showing you this because it's not that important a fact for right now. You should be aware of it. Don't get carried away like people did in the 80s and think you're going to solve the CC problem this way. This is a structure in the leading order in H bar and leading order in alpha prime theory. And like, it's easy to write down a classical zero cosmological constant. The problem is protecting against quantum correction. So this is no good for that. But the fact that is relevant is the potential is 0 for all T. That is a flat direction. So T is not stabilized. You can take T off to be wherever you want. And the Kähler moduli have no mass so far. So we have what looks like a problem in these solutions. So remember, we're studying the 4D EFT of the imaginary self-dual conformally Calabi-Yau solutions of Giddings-Kocher-Polchinski, the GKP compactifications. And in these compactifications, the Kähler moduli are unstabilized. Okay. So we have to do one more thing. Include quantum effects. So now we've understood, hopefully, up to here. Now we have to understand how quantum effects correct the superpotential. And maybe you can already see that once the superpotential does have a dependence on T, you're back to equation counting. It's a function of T. Why shouldn't you be able to find some T where you can solve dTW equals 0, and it'll be isolated? Okay, and it's going to be an easy exercise to check that with this particular form, that's in fact the case. Now, if you so let's look ahead before we do the calculation in the last couple of minutes. If you manage to make all the F terms 0, not just the complex structure moduli and axiodilaton, but also the Kähler moduli, this whole term is gone. But this remains. And so you'll find a vacuum in ADS. You'll have negative vacuum energy, but SUSY. And that's okay, ADS can have supersymmetry. So that's where we're going to find a supersymmetric ADS vacuum. Yes?
So what guarantees that these quantum effects will not destabilize the other moduli?
Ah, very good. Okay, question is, why won't the quantum effects destabilize the other moduli? To a very small level, they will. There's going to be a separation of scales, which we'll get into more next time. This is going to be an exponentially small effect, and at a very high scale compared to where this happens, the complex structure moduli and dilaton get classical masses, big solid classical masses. And then at a much lower scale, the Kähler moduli get mass. That's the story. The complicated version of the story will be told in tomorrow's lecture, but roughly that's how it happens. So there's a question here, I'll take that, and then I'll explain in the remaining 5 minutes where these quantum corrections come from. No? Okay, so all we have to do now in the remainder is understand why does the superpotential have, I'll still want that too. Why does the superpotential have quantum corrections, and why aren't they polynomial quantum corrections? So this is actually sort of a nice structure. Yes, good. Which I've written on a straight piece. Okay. So T is the 4-cycle volume plus I times the integral of C4 on that same 4-cycle, which is, we can write it as real T plus I theta. And W flux is equal to integral G wedge omega with no T in it. And what we want to do from this is figure out what are the possible quantum corrections to the superpotential. Well, the superpotential is holomorphic. So SUSY implies that W is holomorphic. This is just the flux superpotential. What's W full? W full is equal to W a question mark. That's what we're about now. We want to understand what are the possible quantum corrections. Now, what kind of quantum are we talking here? Are we talking the alpha prime expansion or the actual H bar expansion? Right now, for the purpose of today, we're going to talk about the alpha prime expansion. And the alpha prime expansion is a curvature expansion. When things are big, the corrections are small. So and the Kähler moduli tell you how big things are. So that means that if there are going to be any alpha prime corrections to this, they have to go away as T gets big. T gets big, curvature is small, no corrections. So question mark, what if we have some like 1 over T plus 1 over T squared with some coefficients that I won't bother to write, plus some, I don't know, e to the minus 2 pi T, well, we'll worry about the normalization later. Okay, that's our question. And the thing is, you can't have these. They're holomorphic, good, but they're not invariant. So not invariant under theta goes to theta plus constant. So what we'll do now is I'll explain to you why theta equals theta plus constant is a good, important, protected symmetry. But let's just work at a sort of operational level first. Hopefully you believe me that, okay, the superpotential's corrections have to be 1 over, some powers of 1 over T. And they can't have real T. That's not holomorphic. So you just try powers of T itself. There's a shift symmetry that I'm going to describe to you momentarily. And under that, T goes to T plus I theta. So that's not this. And so these terms are forbidden, yes?
Maybe this is more of a supersymmetry question I don't know about. So we said that supersymmetry with the solutions we're looking for is broken, but we're using that supersymmetry applies the superpotential holomorphic to restrict it, correct?
Yeah, excellent point. Okay, so the remark is, if we're breaking a supersymmetry, how can we use supersymmetry? And the answer is, first we're going to find a supersymmetric Lagrangian using all the full structure of SUSY, and then we'll find a supersymmetric state in it. And for that supersymmetric state, everything's good. Then I have to be much more careful once I break SUSY, and we'll do that. Okay, so the last little piece is, so, yes, please.
About 2 minutes?
Yes.
We are taking our photo at the break.
Okay, so I will use only 2 minutes. Tell me when my 2 is up. Is everyone temporarily okay that the shift symmetry would forbid these terms, but it would allow terms like a discrete shift, theta goes to theta plus 1 is totally okay here, right? If theta shifts by integers, you're fine. That's the kind of thing that usually happens with instantons, right? Some shift symmetry that's good to all orders in perturbation theory and that's broken by instantons to a discrete shift. That's what's operative here. And so I just have to tell you two things. What's in 2 minutes, what's the instanton and what's the shift? So the instanton is the so-called Euclidean D3 brane. And it'll be better for me to just tell the full story of this next time, so let me just state in words the business, and then we'll examine it a little bit more closely. Instanton is a Euclidean D3 brane, which is also called, it's a kind of D-instanton. You think of instantons as saddles of the Euclidean action. This is a saddle of Euclidean action that involves a D3 brane wrapping 4 Euclidean space dimensions in the internal space. That's why its action is proportional to a 4-cycle volume. Where does the shift symmetry come from? The shift symmetry comes from the fact that C4, shift of C4 goes to C4. This is related to the gauge symmetry question that was asked last time. This is a gauge symmetry of the 10-dimensional theory. And C4 goes to C4 plus omega 4, which is an element of H4 of XR, so a real cohomology class. This is a global symmetry in which theta goes to theta plus some constant that's real. But the thing is, this symmetry is also present in the 10-dimensional theory, although I didn't explore it last time. And symmetries like that can only be broken by extended objects. You're shifting by a closed form, a topological thing. The only way to capture that is to have something big that can wrap around and detect it. That's such an instanton. And so by that argument, these terms have to be 0. And now let's wrap up. Quantum effects from Euclidean D3 branes give that the superpotential takes this form. And that allows for one to find n equals 1 supersymmetric vacua with all the moduli stabilized. So the potential Vf as a function of real t in these cases looks like the following. This is V equals 0. The potential looks like that. That is an ADS that's supersymmetric. One question, I guess, and then I'll be done. Yeah.
Just defer the questions because we need to go take our photo. So
Okay.
let's thank
All done for now. Yes.
Ask everyone to stay outside. We'll have a short walk.
Like, you can't leave your things here. The mass was like 100 GS.
Whose mass are we talking?
The device.
Yeah, 1 over GS, yeah. But you could write it. You could write it in terms of the Einstein frame volume. So that T is an 4-cycle volume, or equivalently, it's a string frame cycle volume over GS. So definitely, it's morally e to the minus 1 over GS. It's just that I've chosen good Kähler coordinates where the Kähler model.
And you're in the photo too. So.
Thought it. Yeah.